Welcome to all. In part 7 going to present about steam nozzle problem. This is continuation of previous part. In a steam nozzle, steam expands from 16 bar to 5 bar with initial temperature of 300 degrees Celsius and mass flow rate of 1 kg per second. Determine the throat and exit areas considering first expansion to be frictionless and friction loss of 10% throughout the nozzle. Given data, P1 is equal to 16 bar, T1 is equal to 300 degrees Celsius, P3 is equal to 5 bar, a mass flow rate is equal to 1 kg per second. Find A2 and A3. Solution: inlet from steam table at pressure P1 is equal to 16 bar and T1 is equal to 300 degrees Celsius. H1 is equal to 3036.2 kilojoule per kilogram. S1 is equal to 6.887 kilojoule per kilogram. Like that, going to calculate the thread pressure value using polytropic formula. P2 by P1 is equal to 2 by n plus 1 power n by n minus 1. And then from the steam table we know that pressure 2 value. From that we can obtain HF2, HFG2, SF2, SFG2, VF2, VG2 values. From equation S2 is equal to S1 is equal to SF2 plus X2 SFG2. From that we can calculate X2 value, the dryness fraction value. After that we also use the molecular diagram chart to calculate, to obtain enthalpy at 2, V2, H3, P3, and then the throat velocity. If inlet velocity neglected means you have to use C2 is equal to 44.72 square root of H1 minus H2 formula. And then throat area you calculate from continuity equation. M is equal to rho 1 A1 C1 is equal to rho 2 A2 C2. Here the mass flow rate at section 2 is equal to A2 C2 divided by V2. From that we can calculate the area 2 value. Here the mass flow rate is at exit is equal to 1 because already problem has given the value 1 kilogram per second. We can substitute that mass flow rate at the exit area and then we can get the exit area of nozzle. Throat area. And the exit velocity, if inlet velocity neglected, C3 is equal to 44.72 H1 minus H3. And the area at exit from continuity equation, M is equal to rho 1 A1 C1 is equal to rho 2 A2 C2 rho 3 A3 C3. From the continuity equation we can calculate the A3 value and then considering expansion to have 10% heat loss. In the 10% heat loss, going to consider into the nozzle efficiency, throat velocity, where eta is equal to 1 minus friction loss. We are assuming that friction loss means fraction value, some particular due to the percentage of value. So here we know that 10% heat loss. So 1 means that overall complete efficiency with subtract the friction loss means we can get the efficiency, nozzle efficiency. Throat velocity If inlet velocity neglected, we can obtain the throat velocity C2. C2 is equal to 44.72 square root of eta multiplied with H1 minus H2, and throat area from continuity equation M is equal to rho 1 A1 C1 rho 2 A2 C2. And also the exit velocity if inlet velocity neglected, the C3 is equal to 44.72 square root of eta multiplied with H1 minus H3. And the area at the exit is also calculated from continuity equation. M is equal to rho 1 A1 C1 is equal to rho 2 A2 C2 is equal to further rho 3 A3 C3, because mass flow rate will be same at any section in the same flow line. So A3 is equal to M divided by rho 3 C3. From that we already know all the value of the continuity equation parameters except the A3. So from that we can calculate the A3. And then this is divergent nozzle problem. Here is required to discharge 2 kg per second of steam. This is the mass flow rate of the problem. The nozzle is supplied with steam at 7 bar and 180 degrees Celsius, and discharge takes place against a back pressure of 1 bar. The expansion up to the throat is isentropic, and the friction resistance between is equal to N. The throat and the exit is equivalent to 63 kJ per kilogram of steam. Taking approach velocity of 75 meter per second and a throat pressure of 4 bar, estimate suitable area for throat and exit and overall efficiency of the nozzle based on the enthalpy drop between the actual inlet pressure and temperature and the exit pressure. We know the data from the problem. Mass flow rate, pressure at section 1, temperature and pressure at section 3, H3 dash is equal to H3 plus 63 kJ per kilogram, and also the velocity at inlet and pressure at exit. So we need to find A2, A3 and coefficient of velocity. Here the inlet going to calculate from steam table values. So we know the P1 value 7 bar as well as the T1 value is equal to 180 degrees Celsius. From the value you can calculate the PA value, TA value, HA value, SA value, PB value from the steam table. The T1 value is equal to 165.65 degrees Celsius, HP is equal to 2762 kJ per kilogram, SP value also 6.705 kJ per kilogram Kelvin. Because not available in superheated steam table, so we are taking from the 7 bar at saturated condition. So by interpolation we can get the HR value and SR value. Here S1 is equal to S2 due to the condition of the steam, isentropic process. Throat from steam table at pressure P2 is equal to 4 bar, where HF2, HFG2, SF2, SFG2, VF2, VG2 value obtained from the steam table at the pressure of 4 bar, and then from equation the entropy value S2 is equal to S1 is equal to SF2 plus X2 SFG2. Like that way we can calculate the enthalpy value at throat, H2 is equal to Hf plus H2 Hfg, and the exit velocity, if in inlet velocity neglected, C2 is equal to square root of C1 square plus 2000 multiplied with H1 minus H2. Discharge from the continuity equation, M is equal to rho 1 A1 C1 rho 2 A2 C2. We know all the value except the A2 value, area at throat, etc. Mass flow rate already given, velocity already found, x2 and v2 also obtained from the steam table. From that we can calculate the A2 value. Then exit parameter, going to calculate from steam table value. The steam table value obtained from pressure 3 is equal to 1 bar, where we can get HF3, HFG3, HF3, SFG3, VF3, VG3 values. From equation S3 is equal to S1 is equal to SF3 plus X3 SFG3, as well as the H3 is equal to HF3 plus X3 HFG3. From that we can calculate the H3 value. And then the exit velocity, if velocity inlet velocity neglected, C3 is equal to square root of C1 square plus 2000 into H1 minus H3. Area at exit from the continuity equation, M is mass flow rate is equal to rho 1 A1 C1 rho 2 A2 C2 rho 3 A3 C3. From the relation we can find the A3 value, remaining values are known values. If the frictional loss is considered, H3 dash is equal to H3 plus 63. So we know the H3 value, we can calculate the H3 dash value. Exit velocity if inlet value neglected, C3 dash is equal to C1 square root of C1 square plus 2000 multiplied with H1 minus H3 dash. And overall nozzle efficiency is equal to eta n is equal to H1 minus H3 dash H1 minus H3. From that we can calculate the overall nozzle efficiency, and then coefficient of velocity is equal to C3 dash C3 divided by C3. From that we can calculate the coefficient of velocity as steam. Thanks for watching. I will conclude my presentation within this slide, and then I will continue this from next part.